Swayam Prabha. Digital India. Educated India.
Welcome to the 15th lecture in mechanics of materials. In the last lecture we saw 6 different material parameters: Young's modulus, Poisson's ratio, bulk modulus, shear modulus and 2 Lamé constants. Okay. The relationship that we obtained between these various constants is tabulated here. Again basically you had Young's modulus related to the Lamé constants, Poisson's ratio related to the Lamé constant through these expressions, and Lamé constant related to the Young's modulus and Poisson's ratio through these equations. Now what we are going to see is what are the restrictions or what are the possible values that these material parameters can take. Okay. Now what we define for the Young's modulus is, we define the Young's modulus as axial stress by axial strain, which was P by A into delta B into L, right. Okay. So now what happens if I apply L and A are positive, L is positive, A is positive. If I apply a tensile force, I should get a displacement in the direction of the force, right. So P by delta B must be positive, because the displacement should be in the direction of force. If I apply a compressive force, the length will reduce, delta B will be negative. If I apply a tensile force, P will increase and delta B will increase, will be positive, and hence P by delta B has to be positive. Okay. From these restrictions you find that Young's modulus has to be a positive number. Okay. Now the question is, can Young's modulus tend to infinity? If Young's modulus tends to infinity, what you are saying is, even though I am applying an axial stress, tensile or compressive, there is no strain developed. That is the meaning of E being infinity, which is a rigid body. E tending to infinity means the body tends to become rigid, that is there is no deformation even though I am applying a force. Okay. That is, the displacement between two particles is the same irrespective of what two particles I consider in the body. Okay. So since in this course we are not interested in the rigid bodies, what we say is the Young's modulus has to lie between 0 and infinity. It cannot be 0, it cannot be infinity, but it has to lie between 0 and infinity, or it can be a positive number. Okay. A similar argument we make for the shear modulus. Shear modulus was defined as shear stress by angle change caused due to the shear stress. So a shear stress acting like this on a body should produce angle change in the direction of the stress, right. A shear stress acting like this should produce an angle change in the direction of the stress that is acting. Okay. So G has to be positive for the same reasons that displacement has to be in the direction of the applied force. Displacement has to be, since displacement in the direction of the applied force. Okay. Again shear modulus being infinity means, shear modulus tending to infinity means there is no angle change despite there being a shear stress applied. Infinity means no angle change despite shear stress acting. Okay. This means the body is a rigid body, which we are not interested in this course, because we are interested only in deformable bodies. So, the range of G is this, it has to be a positive number. Okay. On the other hand, bulk modulus is defined as the ratio of hydrostatic pressure divided by volumetric change. Okay. Now, again bulk modulus has to be positive, because if I apply a compressive force, the volume should decrease. If I apply a tensile hydrostatic pressure, the volume has to increase. Okay. For the same reason as above, K has to be greater than 0, since displacement in the direction of the applied force. The applied force. Okay. Now, there are some materials which will not change its volume despite what hydrostatic pressure you apply or whatever be the stress state. There are certain materials that will not change its volume. Okay. Such materials are called as incompressible materials. Reals, the volumetric strain is equal to 0 for volumetric strain is 0. Okay. So, K can be equal to infinity. Okay. So, the domain for K is 0 less than K less than or equal to infinity. Okay. So, that is the domain for K. Now, with these restrictions, we want to find what is the restriction of K, G and E on the Poisson's ratio and the Lamé constants lambda and mu. Okay. So, now we have G given by E is given by 2 times 1 plus mu. The shear modulus is given in terms of Young's modulus and Poisson's ratio as that, right. If G, this implies if 0 less than G less than infinity and 0 less than E less than infinity, then nu has to be greater than minus 1, right. Mu equal to the Poisson ratio equal to minus 1 means G is infinity, which is not allowed, and if mu is greater than minus 1, E is positive, denominator is negative. So, G becomes negative. Okay. This is because G has to be greater than 0, okay, when E is always greater than 0. Okay. So, you get the restriction that the Poisson's ratio has to be greater than minus 1. Okay. Now, the bulk modulus K is given as E by 3 to 1 minus 2 mu. Okay. Since bulk modulus is E by 3 into 1 minus 2 mu, it implies that if 0 less than kappa less than K less than or equal to infinity and 0 less than E less than infinity, then nu has to be greater than or equal to 0.5 and nu is 0.5 for incompressible materials. Okay. So, from here you get that then nu should be lesser than or equal to 0.5 and mu has to be equal to 0.5 for incompressible materials. Okay. From these two restrictions, from this and that restriction, you get nu to vary between minus 1 and 0.5. Okay. Mu has to vary between minus 1 and 0.5 from these two restrictions. Okay. Now, since mu is g, the restriction on mu is also from 0 less than mu less than infinity, it comes from this restriction g is that, and hence you get this restriction on mu. Okay. Now, the other Lamé constant lambda is E times nu divided by 1 minus 2 mu into 1 plus mu. For the given range, you know that E is positive, 1 plus mu is positive, 1 minus 2 mu is greater than or equal to 0. Okay. Mu has range between minus 1 and 0.5. All this together would imply that lambda varies from minus infinity to plus infinity. Okay. The equal to sign here is because when mu is 0.5, that is what is allowed, it will be positive. Mu is 0.5, that is when this will be positive, whereas when mu is cannot be minus 1 and hence it can't be negative infinity. Okay. So, to summarize, we have seen that the following are the restrictions on metal parameters. For E varies between 0 less than E less than infinity, G varies between 0 less than G less than infinity, kappa varies between 0 less than bulk modulus is less than infinity. Similarly, lambda varies between minus infinity and infinity. The other Lamé constants varies between 0 and infinity, and the Poisson's ratio nu varies between minus 1 less than nu less than or equal to 0.5. Okay. So, these are restrictions on the metal parameters. Now, we have these 6 metal parameters. Do you need all the 6 metal parameters to describe a constellation? No, you need only any 2 of this subset. Okay. So, you have 6 metal parameters, we need any 2 of the above 6 to describe a isotropic linear elastic material. Okay. What is this isotropic means? We haven't seen. It means that the response of the body in different directions would be the same. Okay. So, that is what we mean by isotropic, and when we wrote that sigma is lambda trace epsilon identity plus 2 mu epsilon, we assume that it is isotropic, assumes it is isotropic. Okay. That is the response in different directions are the same. Okay. So, here we wrote in terms of lambda and mu, we write in terms of Young's modulus and Poisson's ratio, we can write in terms of Young's modulus and Poisson's ratio or bulk modulus and shear modulus. Any 2 we can pick and we can write this constellation in terms of those 2 parameters. Okay. So, to go forward, you have to remember that G is given by the sigma, the stress is given by this expression, and your strain is given by the expression 1 plus mu by E sigma minus mu by E trace of sigma identity. Okay. These 2 expressions you have to remember, and the range of values that the Poisson's ratio can take, the Young's modulus can take, and the Lamé constants can take. Okay. That is what you have to remember to move forward. Okay.